my name is Clara Meister. I'm a PhD student at ETH Zurich, and today I'll be presenting on our work titled, Is Sparse Attention More Interpretable? This was joint work with Stephen Lasloff, Isabel Augenstein, and Ryan Cotterill. So first I'll start by introducing the attention mechanism, focusing on aspects that are relevant for our experimental setup. Now let's consider tasks for which we use probabilistic models, conditioned on some input sequence X. In natural language processing, these sequences are typically natural language. For example, our input in sentiment analysis or conditional language generation. Standard practice a few years ago was to encode this input into a single fixed length vector, which we conditioned our output probability distribution on. Now, this paradigm is not optimal, especially when decoding involves multiple steps for which different parts of the input may be relevant. The attention mechanism partially solves this problem, giving us the ability to use a weighted sum of intermediate representations rather than just the last encoder output. Informally, this allows the model to condition more heavily on information that it deems more relevant to a prediction. Now, one question is, how does our model choose these weights? So, using an alignment function, our model maps a query, Q, and a key, K, to unnormalized weights. K here is typically our stacked encoder outputs, while Q may be, for example, a representation of the question in question answering, or the current decoder state. Now, to ensure that these weights sum to 1, we project them onto the probability simplex using what we'll call a projection function. Now, different projection functions will induce different mappings onto the probability simplex. For example, softmax typically produces a dense set of weights, while on the other hand, the sparse-max projection function, as the name implies, produces a sparse mapping. Variants of the sparse-max can give us even sparser or denser mappings than sparse-max and softmax. Now, the big question in the NLP community has been, does the resulting attention distribution have an easy interpretation? We see that attention provides a mapping, and that this mapping shares indices with our inputs. But does the weight at position t tell us how important the input at position t was in a model's prediction? And if yes, then can sparse attention give us a core subset of the inputs that led to a model's prediction? Now, prior works have assumed that the answer to both of these questions was yes. But recently, some studies have shown that attention may not provide faithful explanations of model behavior. For example, we can often find adversarial attention weights that lead to the same prediction from a model, but suggest an entirely different reason for a model's decision. This observation kind of makes sense when you think about it, though. Attention is over representations that are internal to the model, not directly over inputs. And these representations are not bound to encoding information solely from the input token that they're co-indexed with. In fact, in most neural architectures, all inputs can influence the encoder output associated with a given position. So this raises the question, how strongly related are inputs to their co-indexed intermediate representations? Perhaps if we observe that intermediate representations are encoding information primarily from co-indexed inputs, we would have reason to believe that, for example, sparse attention indeed gives us the ability to identify a subset of influential inputs. This would even be the case if we could link an intermediate representation primarily to any single input, even if not co-indexed. Now, to explore this question, we can look at feature importance measures, which, using gradients or erasure techniques, give us a sense of how influential a particular component was to the state of the output. Here we specifically look at the influence of inputs on intermediate representations. If the distribution of feature importance is generally high entropy, this would suggest that we can't in general link an intermediate representation primarily to any single input. On the other hand, low entropy distributions would suggest the opposite. To test this, we run experiments on 3 text classification datasets using different model architectures and projection functions. We see that the distribution of input feature importance distributions with respect to intermediate representations has consistently high normalized entropy, even when using sparse attention, which suggests that the relationship between intermediate representations and inputs is far from 1-to-1. Now, importantly, this implies that although it highlights influential intermediate representations, sparse attention does not necessarily allow us to identify a sparse set of influential inputs. We next explore this ability directly. Specifically, can we in general find a sparse set of inputs that are critical to a model's prediction? And further, does using a sparse attention mapping influence this result? We can explore this question by looking at the distribution of feature importance measures of inputs with respect to outputs. In a set of experiments similar to our first, we see that normalized entropies of the feature importance distribution of inputs with respect to outputs is generally quite high across models and datasets. Further, using a sparse attention mapping appears to make this entropy even higher. In the final part of our paper, we look back at a previous finding about attention, specifically that attention tends to not correlate well with other metrics of feature importance. We now ask, do these prior findings change when we use a sparse attention mapping in our model? In our preliminary experiments, we confirm prior findings that attention doesn't correlate well with measures of input feature importance. Rather, as we could perhaps expect, the much stronger correlation is with metrics of intermediate representation importance. That is, the entities that the attention distribution is computed with respect to in the first place. Now, this finding holds even when using the sparse max projection function. In fact, the discrepancy seems to be exacerbated. A further analysis of this last observation shows that sparser attention distributions correlate even less with well-established feature importance metrics, which makes it seem that when using a sparse attention mapping, it's perhaps even less likely that attention provides a faithful explanation of model behavior. Thank you for watching, and if you'd like to read more about our experiments and our analysis, you can find the link to our paper here.